Of earth shine. Dun, dun, dun. The word is faint here. So faint. Earth shine, and it's almost like the ghosty part of the moon. Okay. So this right here, this is earth shine. Kind of this dark part is earth shine. Starts with letter C. What sort of phase would we call that? Crescent. Very good. Okay, crescent roll. Anybody know if that's waxing or waning? Go from right to left.
Oh, maybe.
It's waning, yeah, it is waning. So you stick out your right hand, whatever it's doing over here, and sometimes it's tilted a little bit, whatever it's doing over here, it's going to continue doing. So that's a waning crescent. Very good. On its way to new moon. So why do we see that kind of ghosty part? And the word is bounces back. And I have a figure here to kind of show you what that looks like. So, of course, the only reason we see the moon is because the light from the sun is hitting it, and then we're getting to see that back. So, light from the sun, yeah. So here's the sun hitting the moon. Okay, so we see the crescent. This isn't, these are different crescents, aren't they? This is a waxing crescent, that's a waning crescent. So we see a waxing crescent, but the other thing is we actually see the ghosty part because the sunlight is hitting the earth, and then that sunlight is going back, it's backscattering onto the moon. So we see it because of the bit that's going from the earth back to the moon. So that's kind of fun. That's earth shine. So earth shine, it's best when the moon is in its crescent phases. Okay, tides. Anybody here ever lived by the tides? Lived by the oceans? No, not yet. You never know where you'll end up. But of course the oceans, they have the whole tide thing going on. And I'm going to show you that it's actually a gravitational tug of the moon that creates tides. Okay, it's kind of bizarre. And so if this is the moon, and this is the earth. Oh, wow, that's not gonna work. I'm just afraid it's gonna fall over. Try this. So, all things exhibit gravity on each other. Super cool, I'm telling you, super cool, make it all better. Okay, so those large bodies of water actually then lift up when they're on the vicinity of the moon. Okay, looks like closest. So the side of the earth that's closest to the moon is going to experience the kind of lifting the large bodies of water. Side of the earth closest to the moon will experience high tide, and there is a lag of 10 degrees. So this is a good figure to kind of show you. Moon's over here, you can kind of see this. This looks more to me like the Earth's atmosphere being pulled up, but also kind of think of the large ocean, the large bodies of water, the oceans, the Atlantic Ocean, the Pacific Ocean being lifted up. But a weird thing, to me it's kind of weird, is do you see in this figure, it's correct, that even though the moon's over here, it's creating a pull, a high tide over here, there's another high tide experienced on the other side of the Earth. So that's kind of bizarre. So if the Earth spins once every 24 hours, and we figure the Earth is kind of spinning underneath this influence, this tug. So what happens then is we get actually a high tide every 12 hours. Because you get it over here next to the moon, and you get over here away from the moon. So if it was always just next to the moon, it'd be 24 hours for every high tide, but since it's on both sides, it's every 12 hours. So since we're kind of from Iowa and all that, we don't kind of see the whole effect of tides because it has to be a larger body of water from the Mississippi or the Des Moines River. So you can see, you see the little people here? Okay, so this is the same field of view. And so here, this would be at high tide on the left and at low tide on the right. So that's kind of cool. Okay, high tide on the bottom, low tide on the top. And it's like, I guess that's not going to damage those boats, but I'm like, I don't know. It doesn't look very healthy for those boats. Okay, so there's another thing I want you to know about, though. When the sun is in cahoots with the moon, there's an especially high tide. Okay, so when there's an alignment of the moon and the sun against the earth, you're going to have an especially high tide. So that will occur, and that's called spring tide. That will occur in both of these scenarios. Now, I know yesterday we had the earth with 4 moons, but we know the earth doesn't have 4 moons, earth doesn't have 2 moons, earth has one beautiful moon. But here we're showing the moon in 2 positions. This would be in the new moon phase, this would be in the full moon phase. And in both of these, new moon and full moon, the sun is lined up, and that gives an especially high tide we call spring tide. Now, when the sun is working against the pole of the moon, that would be like at right angles, we call that a neap tide. So that happens at our quarters, the first quarter and the third or the last quarter. You're going to get high tide, but it's going to be a diminished high tide we call neap tide. Okay? All right, so we did the whole thing with eclipses yesterday. Now, eclipses occur when there's a very special alignment of 3 things. Of course, we're on the earth observing the eclipse, the moon, and the sun. There's 2 types of eclipses. The name of the eclipse tells you what's being kind of getting darker. So a lunar eclipse, the moon is getting darker. And you hear them talk about the fact that the moon is passing into the Earth's shadow. So we call, this figure has it on it, but we say that whether the moon is passing through it or not, from what the sun is shining on the Earth is casting into space 2 shadows. A really dark shadow called the umbra and a lesser shadow called the penumbra. So we say if the moon passes into the umbra part of the Earth's shadow, then we get a lunar eclipse. You might have heard people talk about a blood red moon, and I've seen just a few eclipses. And at totality is when the moon is entirely into the Earth's umbra or Earth's umbra shadow. At totality, it does turn kind of that cool sort of red color. So the other type of eclipse is a solar eclipse, and that's being shown down here. So a solar eclipse, we kind of have this configuration where we're here on Earth observing it, and the moon is going to pass in front of the solar disk. Okay, that creates a solar eclipse. Like I think I showed just a clip yesterday where we saw the disk of the sun and kind of a bite taken out of the sun because the moon's disk was passing in front of the sun's disk from our perspective. So what phase is this for? Sometimes this makes us in the form of a test question. Up here, let's go back to a lunar eclipse. What phase is that? Full moon, yep, full moon. How about this one right here? New moon, yep. Oops. Find my little pen here. All right, full moon up there for the lunar eclipse, and new moon down there for the solar eclipse. Now, one of the last things I want to talk about with regard to eclipses is this, and you guys did it yesterday. Here's the solar eclipse. By the way, the next solar eclipse is in 2024, I want to say. It's on my husband and I's calendar to travel. We're probably going to go down to Cape Girardeau area, and it's going to be an eclipse that lasts even longer than the one that lasted this last fall. So, all right. So in lab yesterday, you kind of, when you had your moon and your Earth on the yardstick, in order to get your eclipses, you kind of had to tilt it relative to the sun. And that's kind of what we have going on. We talked about the plane of the ecliptic, right? That is the plane that most of the planets are pretty much in line with orbiting the sun. And then we have this plane of the moon, okay? The plane that the moon orbits the Earth. And it doesn't lie exactly in the plane of the ecliptic. If it did, check this out, then we would get, for every full moon, we would get a lunar eclipse, and for every new moon, we would get a solar eclipse. So it's tilted outside just a little bit, so when it kind of is just right, that's when you get your, ecliptic plane. That's the word. So it's tilted outside the plane of the ecliptic plane. So let's be just right. So for the assignment that's due on Monday, you're going to sketch and label phases of the moon in the order that they occur. That'll be good practice. Actually, if you want to put 8, there should be 8 of those. I'm pretty sure that's right. Because there were 7 on the slide before, and you guys told me the new moon was missing. Describe the 2 main features visible when we look at the moon. I'll give you a hint. They're going to be dark and light, and so look up what those are, and then answer those other questions. Okay. Okay. So by my count, we are ready for part 4, and it's a short one. I've got my stellarium here, but I don't know. There's probably not much necessarily to show you. Stellarium. Let's see if I want to bring it up later. Now, if you in the fall, or actually I'm going to teach it also in the spring in the hybrid format. But if you get a chance to take a longer course in astronomy, that would be nice, because there's just so much more than I'm covering here in 3 weeks. But we get a chance to kind of go look at the stars. Now, before we start to look at the stars, I want to talk about this thing called parallax. Parallax, that's the word up there. Sometimes I don't know if it's 2 L's or 1 L, but it's 2 L's. I'm going to show you that kind of a common thing you can do on your own to kind of experience parallax. And it goes like this. Okay, so I'm going to come stand behind you, and maybe we'll look at the same object. So, you guys are pretty close to the screen. So, if we just look at something up in front there, like the corner of, like that. And put your finger, let's see, put your finger on the tip of your nose and cover one eye, blink one eye, and then the other eye. If you go to the eye doctor, actually he will or she will ask you these questions. Does your finger seem to move? Mine does. Kind of depends on how your eyes are arranged. Like I'm kind of closing one eye and then closing the other eye. Did anybody's finger not move? Okay, because we have a dominant eye. For me, I'll ask you a follow-up question. For me, it moves the least with my, I guess it'd be the one that's open. So my right eye, I think, is dominant because it moves the least with my right eye. Okay. All right, so then go ahead and take your finger and look at the same spot, but extend your finger to an arm's length. What's the difference then? You see a difference? Go back and forth. Can you tell the difference? What's the difference? It moves less. Yeah, it moves less when our arms are up there. Yeah. And the parallax part of it is the moving. And we say as an object gets farther and farther from our point of view, it's less parallax. That's just it. That's just it. And so that's being shown here. Here we have two people that are both looking at the same tree that's relatively close to them, and they're looking at the background mountains. So relative to this guy, he sees the tree over here, and relative to this gal, she sees the tree over here. Okay, again, now the tree is kind of like when we had a finger bone, so there is parallax. Okay, now what would happen if they took that tree, and no, they have to use binoculars, but if they took that tree and put it clear up next to the mountain, and they moved from her place to his place, the tree wouldn't move because it is part of the background. Okay, so things close up will move as you relocate your position, looking something close, looking something far away. So we actually can do that with regard to the stars, and it has to do with as we orbit the sun. Now we know it takes 12 months to orbit the sun one time, so in 6 months we were halfway around the sun. Okay, let's see, looks like I had, what words did I? Looks like I have move down here. So if we look at what this diagram's saying, we see the sun here in January near perihelion, the sun in July at aphelion, and if a star is relatively nearby, and that's that special star right there, we're actually going to see it move against the background. So when we're here in January, we see that star here against the background stars, just like they saw the tree, or he sees the tree over here to the right. And then 6 months later, we're kind of like the gal, and we see the star over here against the background. Now, this seems a little bit counter because here in a minute, I'm going to talk about constellations. And constellations are those things that you can hang your hat on. Like, I go outside and I see a set of stars. I can make up my own picture if I want. But if I go out the next night, and even a year from now, those same set of stars are going to look like that. Okay? But here's the deal. If we have kind of a rogue star relatively close, we can actually see it move against the background stars. And that's one way that, depending upon how much it moves, we can do some math to know the distance to that nearby star. That's one of the things astronomers do to find out distances to stars. Okay. So, because now I'm going to segue and talk more about constellations. And with constellations, we assume there's no parallax. We assume that they kind of stay where they are. That program Stellarium that I kind of gave you guys, and I know, see, you've got something and you've got something. You all have, like, do you have anything on your phone yet for stars? Not yet? Okay. There's still time. But the sky maps are usually for our Western culture. What I started to say is Stellarium, that program, you can switch it up and you can go to like Indian culture if you want. In May, and I'll get you information about it, but in May when school's already out and stuff, at the observatory, the astronomy club is hosting somebody to come in from Minnesota, and he is actually into Native American like sky lore, and he's also into Indian mounds, but I think he's an astrophysicist. I'm not quite sure. We're looking forward to his speaker. My point was that other cultures see different things. Our culture, I'm going to show you a list of them here in a minute. You're going to see a list of constellations. You're like, oh, I know, I've heard of that constellation. All constellations is a set of stars. Like the slide says, now the sky is chopped up into 88 pieces, but the 88 pieces are not all the same with regard to area and how many stars are in them. I know at the observatory it's kind of fun where we'll have, especially the little kids, just so uninhibited, it's wonderful. And they'll be like, well, I see I see a dog there. I see a snowman. Like, yeah, I see a car. You're like, yeah, I can see that. I see a dinosaur. You know. Okay, but for us, we're kind of stuck with, talking about the Greek and Roman stories. We've got a lot of different talent out there in the astronomy club, that kind of comes out on a given night to meet the public. We've got one guy that tells wonderful stories about, the ones you might have heard of, like with Zeus and the different gods and goddesses. And they're linked to what we see in the nighttime sky. Now, sometimes you're like, really? Does that look like? It just doesn't look like that. So here are the 88 names. And I don't know how much I will be able to convince you, but you probably already figure if you go into the southern hemisphere, you're going to see a different set of stars than you see in the northern hemisphere. It just is. It's just the way it is. So, hollow sphere is the word there. On my list of things, and I should go ahead and do it, is to request that the school buy another one of these things. It's called a celestial sphere. It's cool. My other one, and I didn't bring on purpose anyway. I think it just was very old. And it looked like plastic on the outside, and it had little stars printed on it. And then on the inside was the little earth. And remember that Ptolemy, goodness, I mean, we used to think that everything orbited the earth, and we know that's not true now. But we still stick with the celestial sphere model because it kind of is representative of kind of how those stars stick together in a kind of on the outside or inside of a hollow globe outside with the earth in the center. So the earth is placed in the middle of the celestial sphere. I just like saying celestial sphere. And you can kind of see on the celestial sphere that looks like the sun goes around the celestial sphere. And we know, it's a model. Again, it's not the real deal, but, So movement of the stars then occur because the celestial sphere rotates. And we know that's not the real. In fact, a really big drawback of the celestial sphere would suggest that all the stars are the same distance from the Earth. No. That's not it. But I will say that the far majority of the stars are so far away that when we change our position around the sun, we don't see any parallax. Okay, so that's kind of like if you take your hand and make it part of the wall back there, and you kind of close one eye and the other eye, you're not going to see it move. Okay. So one of the things we talked about earlier in this unit was this idea that Earth's axis of rotation is tilted towards the star called Polaris. Now, one of the things we ended with that part was that it won't always be the star called Polaris, that it kind of does this thing called precession. All right. Again, the plane of the ecliptic, that's going to be on your test on Thursday somewhere. Plane of the ecliptic is kind of that frisbee, that plane that all the planets orbit the sun on. And the Earth's axis of rotation is tilted 23.5 degrees from being straight up and down. And I didn't include this on your test because I'm starting to think, okay, I need to get the test made up for this semester. But what astronomers do, and it makes sense, is if we want to talk about a star or a nova or a comet or something, we basically give the celestial sphere coordinates. Just like we have coordinates like a longitude and latitude on Earth, we have corresponding right ascension and declination on our celestial sphere. So you can kind of say, well, I saw that object there. And all astronomers or astrophysicists can know where they saw it in the nighttime sky or daytime sky. So I just have just a few consolations. Again, this is something that's going to work out this semester for us to do. Although I mentioned earlier that you can go to the observatory, and we have it coming up. It's April 5th or 6th. Oh no, it's a Friday. The first Friday in April. 6th. Thank you. And so April 6th, and even if it's cloudy, I'll be there. Whatever our start time is, in case you want to come and get a tour. And I hope it's clear. A lot of times students have a sense of, looks like the words were bowl and pointer. Bowl and pointer. Bowl and pointer. The Big Dipper. Anybody in here seen the Big Dipper? It kind of looks like this. And the Big Dipper is relatively bright, and it's also what we call one of those circumpolar circumpolar constellation, which means that just from our latitude, because remember, our latitude is the angle that Polaris makes with the horizon. So we're about 42 degrees. Actually, the Big Dipper is something that we're always going to see. Always going to see. Sometimes it's here, sometimes it's here. So we're counterclockwise around Polaris. So if you can find the Big Dipper, then you have a fighting chance of finding Polaris. So in the Big Dipper, we call this part the handle, and then this part the bowl. So we can use the bowl stars. There's 4 bowl stars. We use the 2 farthest bowl stars from the handle, and they will point up to Polaris. Okay, and actually, I have kind of a myth here. Polaris is not a very bright star. It is totally not a very bright star. It's an important star. Oh, you guys got it. We got time. Do you guys ever use Shutterfly? It's so Shutterfly. It's my husband teases me because you can get things printed free, but you know, I don't know, they get you with the shipping, and then they get you with the stuff. So they have these free things, and so this is one of the pictures I took, and so in the center is Polaris, and this is one of those where I think I said before where you open up the shutter and you can kind of see the star trail. So, cheesy. But anyway, so there's Polaris, which is quite appropriate. So it's not the brightest star, and sometimes it's hard to find, but if you can find the Big Dipper, again, you can use the the 2 farthest bowl stars to find Polaris, which actually then Polaris is in what we say the handle of the Little Dipper. Now, the Big Dipper and the Little Dipper actually are just, they aren't constellations, they're what we call asterisms. Okay, they're like sub-constellations. You might have heard of the Big Bear, and that's Ursa Major. Big Bear, Ursa Major, right? Major would be big, Ursa must be bear. Okay, so the Big Dipper is part of the Big Bear, and the Little Dipper is part of the Little Bear. And you can find a few other stars from there. Okay, so again, throughout the evening, if you find Polaris, you can count on stuff moving counterclockwise around Polaris. I have a few other constellations to show you. Those red marks actually are showing you the boundaries between the constellations. Again, you kind of see they aren't different sizes. Canis Minor would be Little Dog, and that's the little dog to the constellation Orion, the hunter. Orion is wonderful. Orion has these 3 stars we call the belt stars. It has these swords, the sword here, and it has an awesome what we call nebula there. So Little Dog and Canis Major would be Big Dog. The star Sirius is a very bright star. So Winter Triangle, I'll show you the summer triangle here in a minute, but if you see these dots, from Procyon, to the bright star Sirius, to Betelgeuse in the constellation Orion. That makes up the Winter Triangle, which is going away. Here's the summer triangle. This isn't even an asterism. So this winter and summer triangle deal with 3 stars and 3 different constellations. So we have Vega in the constellation Lyra, Deneb in the constellation Cygnus, and Altair in the constellation Aquila. One of the things, and it's on my husband's list of things to do, if you're wanting to become more familiar with the constellations, the best thing is just to get out there. And on Monday, I'll try to remember to bring you a constellation map for the month of April. They're free. Everything's a lot of free things these days. Okay. One of the things before we move on is we're going to talk about our galaxy. Oh my gosh. Seems like forever when we kind of started trying to put things in perspective with regard to our star and our solar system. And then actually our star is a member of a galaxy of stars. We call the Milky Way. So when somebody says the Milky Way, actually it looks, if you get binoculars, it's tiny, tiny, tiny stars. Here, tiny to us because they're so far away. It makes the Milky Way. So this will also be due on Monday. And we are going to start in on that next part. We definitely won't get through this part. Let's see what we got. Okay, so Buzz Lightyear, right? This kind of dates me a little bit when I put this set of PowerPoints together. But a light year, I know we think of the year as time, and it totally is. But if somebody says a light year, that means the distance that light will travel in 1 year. The distance that light will travel in 1 year, that's it. So if I were to be in conversation with somebody that is on a planet that is 1 light year from me, and they turn on their light, leave the light on, and assuming that it can be powerful enough, not be diluted by traveling to me, it would take 1 year for me to see that turn on. If it's 1 light year away, he turns it on or she turns it on, and it's 1 year later that I see it. That's how that works. Yep. So a light year then, in terms of miles, we talked about big numbers and using scientific notation to pack up big numbers. So 5.88 times 10 raised to the 12th power means I take that decimal and I move it over 12 places to the right. And that's how many miles 1 light year is. Okay. So let's we usually use light years to talk about things like how far away a star is. But if we were going to use light years in terms of the distance from between us and the moon, you're talking 1.29 light seconds. 1.29 light seconds. So somebody on the moon turns on a flash or something happens on the moon, there's a delay of almost 3 seconds before I see it. Well, how about the sun? It's 8 light minutes from the Earth. You might have watched documentaries or whatever that would say if the sun were to go away, to vanish, to cease to exist, it would take 8 minutes before we knew it was gone, because it's 8 light minutes away. Well, Mars is a very busy place. Some of you might have seen the movie The Martian. And there's definitely a delay that light, or when I keep saying light, one of the things we covered in our physics unit was the fact that light is only one member of a family of energies called electromagnetic radiation. So all forms of electromagnetic radiation travel at the same speed. So it's about 13 minutes for light to get from Mars to us. Okay, well, let's leave our solar system and let's go to the nearest star, Proxima Centauri. That actually is a star that a movie was made about. What was that? It was the tall blue people. Avatar? What? Avatar? Avatar, thank you. Avatar. So the closest star is 4.3 light years away. Okay. One of the things I want to talk about in part 6 in here is kind of a little bit talk about our galaxy. So when you see that spiral sort of thing, that's probably our galaxy. We can't get a picture of our galaxy because we can't get above. We can look at the other galaxies. But anyway, if we were to travel to the other side of our Milky Way galaxy, and I'm not sure that this is consistent with what I thought it was, but I'll go with it. 52,000, that's 52,000 light years. So there's definitely a delay. So one of the things we're going to talk about is when a star blows up, they call it a supernova. So the thing is, if we see a supernova on the other side of our galaxy, that event, by the time we see it, it really happened 52,000 years ago. That's how that works. There's that delay. My goodness gracious. Up here, and sometimes in astronomy, we kind of talk about something called a parsec. Sounds like Star Trek-ish, right? And as it turns out, 1 parsec is 3.26 light years. This actually is a slide from our sun being born, or a figure, excuse me, from our sun being born. When we talk about our sun being born, we call that the condensation theory. Sometimes it's called the solar nebula theory, but the condensation theory. So when water condenses, usually condenses from a gas to a liquid, that's kind of what we're talking about. It cooling down, coming together. That's what happens with gas molecules to become a liquid. That's where the word condensation comes from. So, and I think I mentioned this when we were talking about our sun, all stars do this. All stars have this same pattern. And oftentimes a bunch of stars can be born in the same kind of stuff, and we call that big, it's called a stellar nursery actually. We call that big place of stuff that can have a bunch of stars being born at the same time. We call that a giant molecular cloud. So when I think of space, now that could be space within our galaxy, or even more so, we're talking about, you might imagine there are other galaxies, the space between the other galaxies. Most of space is empty. It really is. So when you hit a nebula or a giant molecular cloud, you know you really hit something. What happens then is that, oops, it looks like I have star clusters. I'll put all this up here. So I have clusters, and then the last word up here is companion. So you have this giant molecular cloud that's going to go ahead and give birth to bunches of stars. Those bunches of stars are called a star cluster. So this is a kind of a classic sort of star cluster. This is called the Pleiades or the Seven Sisters. Sometimes through binoculars they look like a little river. Okay, so you can almost see some of the kind of that remaining gas that has not been associated with the star. But those are relatively new stars. It's a set of stars. We actually call this an open cluster. This over here is a cluster of stars too, but it's called a globular cluster. So if you're out viewing any night in an observatory, they might put it on an object, a set of stars. They either call an open cluster or a globular cluster. Just a set of stars that were born at the same time out of a giant molecular cloud. Think of it like that. Another thing about stars is, and this kind of makes sense if you figure they're kind of born together, oftentimes they can have a companion star. So up here, I have a photo, it looks like one of my favorite sets of stars. So this is what we call a binary star system. There's a star, and it has a companion star. Okay. So they're born about the same time, and so gravity is kind of where they're at now. There's been like a Star Trek episode, I want to say, where on a planet it has 2 suns. Could happen. Okay. So most stars, I've heard as much as 2/3. When we look at a star, if you look a little closer, it's actually got a companion. It's gravitational hanging out with it. One of the things I don't like about my Shutterfly, my cool little thing with Polaris in the middle, is it doesn't adequately show the colors of the stars. They're all like kind of greenish, whitish. Now, on a given night, this isn't what I see either. This was taken probably by the Hubble Space Telescope, but if you were to get a good view of it, you can actually see all sorts of different colors in your stars. So we can see different colors, we can see different intensities. And if you're an inquiring mind, you're like, now why is that? Well, it comes down to the third word there is chemistry. It kind of comes down to there must be some sort of different phenomenon happening with those stars to be different colors and different intensities. So there's different chemistry happening in their cores, and I want to kind of briefly touch a little bit on not all stars will have kind of the same pattern to their life. Like stars don't live, they don't breathe. Well, they come into existence and they actually have a finite life. They'll run out of fuel basically. So they'll have a different pattern to their life. They will end their lives differently. And if you want to circle the word mass, this is actually going to show up in a lot of this lecture coming up. So it's all about the mass that the star gets at the beginning of its life to spend or use during its life. I've seen it described as like poker chips. That's its mass. So with relatively low mass, with less mass, in general, now there's kind of some exceptions, but if you see red stars, now red stars are generally kind of dimmer, so it's hard to see red stars sometimes, but oftentimes they are relatively low mass stars and they will live a very long life. We're going to talk about the age of our galaxy. We're talking the age of the universe, which the universe are all the galaxies, okay? And there are stars that have been ticking ever since they were created. That's these red low mass stars. And they will end their lives pretty quietly. Well, at the other end of the spectrum we have are more massive stars. So instead of red, our more massive stars are going to be blue or whitish. They don't live long lives, they live relatively short lives, and in contrast to their low mass stars, they don't go out quietly, they blow up. So I mentioned supernova events, and these are the guys that are going to go out. That's I think, that's a good place to stop, because then the next couple of slides kind of go together. So, very good. Let me know if you have any questions, and hope for clear skies.